Hey folks, what's up? So, we are finally on to the lab manuals that are very, very useful. You'll notice I got a little, just to make you, aware that normally extra files are things you can kind of ignore, but not this week. This is, the lab manual that we'll basically be using. I've modified it a little bit, but you'll notice who's the author on this? Professor Schuss. So this is yeah, very, very well done. A few modifications just in the experimental section that will save you some time, giving you exactly the things. Okay, so um, even though amazing lab manual, as you all know by now, I feel it is my duty to make sure you understand every single, like, where does equation one come from? That's kind of, that seems a bit intense. Where the heck did that come from? So that's what we're going to be doing. Now, unfortunately, this lab takes a pretty big gap. So, photoelectric, chapter 3 in our textbook, Frank Hertz, chapter 4, Bragg, electron diffraction, chapter 5, all modern physics. You don't need the full quantum mechanics treatment. For this lab, technically you would. So going through all of chapter 6 and 7, basically solving the Schrodinger equation in three-dimensional spherical coordinates, um, would be a long time. So let's not sit here for 3 hours. I'm just going to summarize um, everything from those chapters that we would go through if we were, being as rigorous as possible. Basically, my objective is to just I'm going to like summarize some of the equations that we would be completely deriving and figuring out what they all mean, um, and just kind of showing them to you and where they are in the textbook. Because this lab does rely on very little of that. It really just relies on the idea of quantum numbers, um, and selection rules, which we can talk about a little bit, but not too much. Selection rules is a little bit more matrix interpretation of quantum mechanics, which is even more so than wave function probability stuff. So let's save that until you're in the full quantum mechanics course next year. So let's just try to keep this as modern physics as possible. Like your first. I looked at the syllabus for 3400, and you do cover these, but um, you know. Let me try to. Never mind. I was going to show you some good quantum mechanics memes about Feynman quotes. People, no, if anyone says they understand quantum mechanics, they don't understand quantum mechanics. So you've seen it at least once before. Hopefully, just seeing these equations will be a little bit of a reminder, instead of making this already. You know, I'm already quite pedantic about you guys understanding the theory of the phenomena that we're seeing and how we're actually going to investigate it experimentally. Um, if I were to actually solve the Schrodinger equation, you would not like me. So let's just summarize some of the developments from chapter 5 to chapter 7. Let's start off with what the heck is a wave function? That comes about right around here, the end of chapter 5, 5.48, and kind of talking about the wave function and the idea that, how people solve the particle wave duality was to say it's a wave, but the probability of observing the wave, like how concentrated the wave is at a particular moment, that can give you the particle description. Oops, over here. Schrodinger wave equation jumps to chapter 6, right here. And this is the potential that the object is experiencing. And this is the wave function as it changes in time and space. Coulomb potential, that's the potential that we would be using in this case. A little bit more complicated for non-hydrogen atoms, but the hydrogen atom description can be applied to quite a bit of things. So here we go. Experiencing a Coulomb potential. And then right below, we've got the actual Schrodinger equation in 3 dimensions. So once we start getting in 3 dimensions, we've got spherical dimensions. So r, theta, and phi. So the first step in solving this is to kind of do a separation of variables type of thing, where you're trying to solve for this function and you're saying it's a product of different functions that depend on all those 3 spherical variables. So let's kind of yeah, let's not do that. Let's not solve the Schrodinger equation in 3 dimensions. These words may elicit some math physics slash depending on how deep you went into this in modern physics, some PTSD. They're they're intense. So let's just look at the solutions. Um, these solutions to these equations require quantized values. So those quantized values, we call them quantum numbers. They are N, L, and ML. There are more beyond that, like spin and things like that. But for the normal Zeeman effect, not the anomalous Zeeman effect, I'll mention that a little bit because that's one area. The lab manual, I think, the reason this is J is because it's completely generic for uh, L, and the next quantum numbers over here would be S. We are not going to be working with J or S. So every time you see a J in the lab, you can just replace it with an L. We'll circle back to that later. Okay, so solutions, where are those? Solution to the radial equation is table 4, 7.1 right here. Those are normalized exponentials. And then the solutions to both the angular and the azimuthal part of the equation, those come from or they come in the form of spherical harmonics. There's a few of them. Again, not I don't think it's worthwhile to uh, explain why they have that solution. Just kind of fill in the gaps as much as I think is needed. And that equation for the spherical harmonic kind of looks like this. It's basically we're taking that combination of splitting things apart, and it turns out that those two can be solved by one well-known equation, the spherical harmonics. And then we take those solutions and we apply boundary conditions, which are actually way earlier. Those were in, I think, chapter 6. Page 206, 206. Basically normalization, continuity. Yeah, continuity, approaches zero at infinity, normalized, finite everywhere, all sorts of things like that. Okay, so let's actually get into what these quantum numbers are all about. This one you may remember from when we did the well, all sorts of things, the Frank Hertz in particular. This corresponds to energy. So E0 is the ground state energy. Let's look at, we don't need to go back to that. They're the identical equation. 721 is where that is discussed. There we are. And all these values, these fixed values based on these boundary conditions and those solutions, the radial solution and the spherical harmonic solution, they fix what these numbers are. So here's a summary of those fixings. N, positive integer, unbounded. L goes from 0 to 1 integer below n, and ML is basically what it's dependent on L. So let's say L is 2, then ML would be -2, -1, 0, 1, and 2. Goes all the way from negative L to regular L. And L corresponds to angular momentum. In this particular case, we're talking about, electrons orbiting, so orbital angular momentum. And the formula for this, again, comes from the kind of boundary conditions, and the solutions to the 3D spherical harmonics comes in the form of this, where H is the reduced Planck's constant. So I should have written that as an equation. H bar is equal to H divided by 2 pi. We'll use that later on, so that'll come up eventually. That is equation 7.22 right here. And then the Z component of the angular momentum, this is the magnetic quantum number. So that's mostly what we're going to be working with today. That is 723 right here. Pretty interesting phenomena here, space quantization. Um, This is just kind of a nice lead-in, not, not necessary. It does explain a little bit more about what these letters mean. You'll notice S is 0 for everything, so that's why I'm explaining. You don't need to worry about J at all throughout the lab. So these S, P, D, and F, they stand for something. They stand for sharp, principal, diffuse, and fundamental. All those names, this was on 270. Oh, it's right here. They come from uh, spectroscopy research, circa, the late 1800s, 85 to 90. Balmer, like the Balmer series, and the Rydberg formula. Rydberg atoms are like a big old research topic. I actually worked on those in college. So I think this is a nice lead in because it explains what we're going to be observing. We are doing spectroscopy in this lab. So let's add on a little bit to what we did in the Frank-Hertz experiment because with the Frank-Hertz, we actually didn't see spectral lines, but we could have. Remember, there was another source. We did mercury. If we had done neon, which I just, the photoelectric effect was so disproportionate in terms of the setup that I tried to simplify Frank-Hertz as much as possible. And the neon would just be more cables and uh, busy work, to me personally. Okay, so let's a little bit of a reminder what the Frank-Hertz thing is because it is what will be the tube was much bigger and inside this big giant uh, heat oven for the Frank-Hertz one. For us, it's not in a heat oven; it's in a magnetic field, but it's the exact same thing, just a smaller tube. And I'll show you that tube a little bit later on. So just a reminder, we're applying a high voltage so that the electrons are ionized thermoionic emission. They come out and then they are now bombarding whatever atom that we've vaporized inside this vacuum tube. If the electrons have sufficient energy, they will collide with these atoms and excite the electrons in these orbital levels to higher energies. So we didn't really talk too much about this in the Frank-Hertz thing because we weren't going to see this effect. But let's just talk a little bit more about what's actually happening. So bombarding electron comes in. So let's just say this electron was in the n equals 2 state. Comes in. If it has sufficient energy gap between those two levels, then the electron will either just completely stop, or if it had more energy than that energy gap, it will just ricochet away with a smaller energy. So now this electron has jumped to this excited state. That excited state is very unstable. So it will be in that state for a fraction of a second. And in that second, it will drop back down to its original state. And in the process of doing so, energy doesn't go anywhere. Energy just transforms. So where is it going? It's going to the emitted photon. So the energy of that emitted photon is equal to the gap distance between those two energy levels. So if this n equals 3 was the excited state, n equals 2 was the original state, the gap between those two things would be the energy of the photon. And then using the Planck formula for energy that we used in the photoelectric effect, the energy of a photon is Planck's constant and the frequency of that photon. So let's do a little bit of work here to change that to something that will tell us about what we're observing. So let's switch this to wavelength. It's a little bit easier. Usually, wavelength is what corresponds to colors, at least what we're used to. The most common way to talk about colors. So let's switch this around. Remember how we did this in the photoelectric effect. Velocity, distance, time. Distance for waves, wavelength. 1 over time would be the frequency. So velocity is always c. Distance, wavelength, 1 over time would be the frequency. So we can rearrange that formula for the frequency and plug it into this equation, and we end up with this. So that wavelength right there will tell us about the color of the emitted photon. And it depends on the size of the energy gap. In our Frank-Hertz experiment, and this is just a little bit of a conversion so that we don't have to worry too much about units. If you were to express that in terms of electron volts and nanometers, that's what the number would be. So just a very convenient number to work with. So let's just use that. In our experiment, we were looking at a 4.9 electron volt energy or volt difference on the ramping voltage was when the mercury was or when the electrons had enough energy to excite the mercury beyond that, in between those two gap levels. So if we solve for the wavelength in this situation, it ends up being in the UV range. So we did not observe that. You could stare at the heat oven and look at the mercury, you would not see any lines in there. However, if we had done part two, which was neon, just again, more cable spaghetti, kind of busy work, in my opinion, especially given how simple the photoelectric effect lab was, the dips would have occurred not at 4.9 volts, but 2 volts. So the energy gap is 2 electron volts, not 4.9. This we would have seen. This is in the orange red area. So we would have seen lines corresponding to those energy gaps. Okay. So in our situation, identical setup. We're not, there's no like um, extra thing over here. There's no grid creating that like decelerating voltage. We're just looking at a situation where we're trying to view the emitted photons. For us, our source is not mercury, but it's cadmium, and the energy gap that corresponds to is corresponding to a wavelength of 643.8 nanometers, which is a red line. So as soon as you turn on both the power supplies, you will see the red lines. I'm saying lines. Like why lines? Why are there multiple lines? It's diffraction. So our apparatus has just a bunch of very, very intricate optics in order for us to turn the incredibly bright cadmium source, uh, which is dangerous. It emits a lot of UV radiation, so do not look at it. Hence the cardboard shield that will be let's see if I can show you the picture. It'll be in the video, the experiment video later. Um, oh, someone took the cardboard off for this picture, so never mind. Don't look at that picture. Yeah, so I've already leveled the telescope. This is the telescope right here. This is the telescope. We've got some polarizers in here, and inside this telescope is the device that's causing the diffraction. We'll talk about that in a second. So you do not need, I've already leveled everything. You don't need to spin any of these dials down here that they mentioned in the lab manual. I've already done that for you so that you don't have to look directly into the telescope. The camera is already on, so it will observe the effects. You don't have to look anything. I also put some safety glasses on and took the shield off to show you what it looks like because it is kind of cool. So you're not tempted to look at it because it's dangerous to look at. So let's check out what the inside of this setup looks like. Looks kind of like this. We've got our camera out in the front, got a bunch of lenses to focus things. This this is really the only thing that we'll be adjusting throughout the lab. Just spinning that dial. And in here, this plate right here is the thing that's causing the diffraction pattern. So let's talk a little bit about that. Oh yes. Also, do not touch any of the cables. Very, very high currents. Everything I've everything's plugged in. I've already done everything. All these things back here, do not touch those. Everything's already plugged in. The only things you need to be touching are, it's kind of hard to see. This dial right here has some black Sharpie lines on it that you'll be spinning. That's the one power source uh, on-off switch. Here's another power source on-off switch. And then this should be spun all the way to the right. And why is that? Because if you spin all the voltage all the way to the right, that light will light up and then you have control over the current. And the current will enable us to determine what the magnetic field of this is. I believe it says something in the lab manual about rotating the coils. Don't do that. They can get hot. I've already rotated them so that they're in this configuration. Okay, so where is this diffraction coming from? It is coming from this thing called the Lermer-Grunke plate, LG plate. Um, the other way to say plate, commonly it's called a LG interferometer. So you'll see down at the in the citations of the lab manual, that is what it's called in this original source for this. So that makes it a little bit, it may make us click. Oh, okay, that makes sense because we've already used an interferometer and we know that that creates diffraction patterns. This one is just way more compact. No mirrors. It's entirely related, or it's entirely based on geometric optics. There's a nice figure in the lab manual for it. There it is. Pretty crazy. We'll get back to that a little bit. Okay, so before we get into more of the geometric optics of that thing, we're not going too deep in it. You'll see why. Let's circle back to the actual phenomena that we're observing. So basically, the lines that we're going to be seeing, the diffraction pattern, bright fringes that we see corresponding to this wavelength, are going to be changing. There's going to be something weird happening to them due to turning the magnetic field on. And how do we do that? We increase the current. So first up, a little bit of a E&M refresher. I've put some slides in here to just give you a kind of a refresher. The last time I taught something that was related to this. I think I've drawn sufficient figures. There's not really I don't think I need to have this up as we're discussing it. These figures are just a little bit better. I made them with PowerPoint instead of drawing them. Yeah, there's nothing particularly needed in this. But yeah, if you want more information on that stuff, feel free to check out those slides. Okay, so dipole. Just like a electric dipole, magnetic dipole is something that has orientation. Electric dipole orients to an electric field. Magnetic dipole orients to a magnetic field. In this case, we're not looking about an external. We'll talk about that in a second. But a magnet creates its own magnetic field. So it kind of looks like this. Magnetic lines come out of the North Pole into the South Pole. So we're orienting the magnetic moment, dipole moment, in terms of the direction of this kind of where the magnetic field lines are coming out of. So that's the reason it's in that direction. This A vector, right, I, that's just a number. It's just the current. A is something called an axial vector. So basically, if you have an area, the normal vector to that area is an axial vector. It's just like if you have a spinning wheel, the angular velocity, that's a vector too. That points out of the wheel. So if the wheel's spinning like this, angular velocity is that way. You can do it in the exact same way as like the current right-hand rule. So if I take my fingers and I curl them with the current, where's my thumb pointing? Up. That's the direction of my axial vector. Okay, and so just like, actually, yeah, some of these slides are actually kind of nice, especially for the torque one, because it kind of shows the um, difference between regular. So electric dipole, negative will want to go in the direction of the electric field. Positive will go in the opposite direction. So we've got, or I'm sorry, completely wrong. Reverse those. Positive goes down, negative goes up. Where's that slide up there? Oh, here we go. Okay. So electric dipole orients with electric field, spins that way to the, what is that? Clockwise. And same thing with a magnetic dipole, orients to the external magnetic field. So definition of electric dipole, charge, and the kind of I don't even know what you would call that vector. It's not an axial vector. It's more so just something that's oriented in a similar way to the north-south pole. Goes from negative to positive. Same thing with the magnetic moment. Goes from south to north. kind of those like that analogy between South Pole and negative charges and North Pole and positive charges. So sorry if this is too much of a refresher. I know you guys are most of you are in E&M right now, so um, but at least in my experience, E&M the upper level E&M kind of jumps straight away from this and goes into really complicated Maxwell equation stuff. So I thought maybe it would be a good refresher from your intro courses. So this is a torque that the object experiences. And next thing we're going to do, instead of just a bar magnet, let's envision this as being like, what does that look like? A current going around like this, where do currents come from? Moving electron charges. So what we can do is analyze this in terms of the system that we're working with, atoms. So this is an electron orbiting around an atom. So let's try to investigate how we can talk about this in terms of angular momentum. Because remember, angular momentum is definitely something that we're talking about in the 3D Schrodinger equation. Okay, so let's try to relate this. We've got angular momentum is r cross linear momentum. So how do we do this, right? Point your hand in the direction of r, curl your fingers in the direction of p or v in this case. Thumb is the direction of the magnetic angular momentum. So in this case, if our electron is orbiting like this, and this is the opposite direction to the figure above, just because I wanted to make this look identical to the figure in your textbook that does this, like that. So electrons orbiting around in that direction. So what does that mean? That means the current is going in the opposite direction, right? Ben Franklin had that annoying convention to say that current goes in the opposite direction to where electrons actually travel. To be fair, he didn't know electrons existed at that point, but it's just annoying that we haven't switched it at this point hundreds of years later. So we've got an electron orbiting. If we're staring down at it, it would be counterclockwise. So we've got a velocity, linear velocity is just pointing straight away from that. Should have made it a little bit more at a right angle. So we've got R pointing out, V pointing in, L going up. So L goes up, but based on the direction of our current, if we use the same like current right-hand rule, I'm curling my thumb with the current, axial vector would point down. So now we're realizing that the angular momentum and the magnetic moment are opposite to each other. So what we're going to do now is basically try to start with this equation and try to express it in terms of the angular momentum of the orbiting electron. So let's start plugging some of these things in. What is current? It's the change in charge over the change in time. And I'm just dropping the vectors here because based on this analysis right here, we already know that these two vectors are pointing in the opposite direction. So at the end of the day, we'll just stack some vectors back onto these objects that deserve it, like the magnetic moment and the angular momentum, and then we will check that there's a negative sign somewhere. Okay, so what is the change in the charge? It's the charge that's actually going around, the charge of an electron, negative E. And the time is how long it takes the electron to go around in a circle. That's a period. So if it's going around in a circle, the distance it covers is the circumference, 2 pi r. And the period is just this letter capital T. So rearrange this a little bit. We've got 2 pi r over v. And now let's plug that in to our equation up here. We've got negative E for the charge that's changing. We've got 2r over v for the period. And let's do a little bit of algebra. What is the A? A is just the area of the circle that's the electron is traversing. So pi r squared. We can cancel some things now. We've got a fraction in the denominator. So let's leave the 2 pi r in the denominator and bring the v up into the numerator. So looks like our pi's are canceling and this r down here is canceling, and then one copy of r up here is canceling. Okay, so now we have v, and what do we know about angular momentum? It depends on v in some way. So let's try to work this out. In our case, that's what I meant about I would have liked to have drawn that a little bit better so that it's clearly at a 90-degree angle. But if something's moving in a circle, the velocity vector goes out at a 90-degree angle. R always comes from the center. So the angle between these two things, instead of remember, we're dropping the the vector here. We're just going to tack that on at the end. So R cross MV, that's a little, the resolution on this isn't as great as I would like. That's an E, the mass of the electron. And because these two things are at 90 degrees to each other, the cross product magnitude we can use. So instead of RP, it would be RP sine theta. Theta, 90 degrees, so sine of 90 is 1. Now we can rearrange this a little bit and solve for V so that we can plug it into this equation up here. So what does that look like? Multiplying by this value right here. And then what happens? R's cancel, and we're left with this expression. And then I'm just putting the vectors back on the things that deserve the vectors. These are all just constants. That's a vector. That's a vector. Look at that. There's a negative sign. So they are in opposite directions. Okay. So now what we have to do, we're ultimately going to try to figure out these lines that we're seeing correspond to energies. How much does the energy change as a result of being in a magnetic field? So one thing we need to do is figure out how much potential energy a magnetic dipole in a B field has. Just like how much mass or how much potential energy does a mass have being in a gravitational field, or how much energy does a charge have being in an electric field. So a few mechanics reminders. Work is the change in kinetic energy. Work is the negative change in potential energy. And just like with gravity and electric fields, we can always, and this is a special thing about the potential energy, we're free to set a reference point for zero wherever we want. For gravity, we usually set it at the ground, or depending on our problem, if I were launching something off my table, maybe I want the table to be zero or the ground to be zero. You can do whatever you want. So electric, we usually do the negative terminal of the battery. With this one's a little bit, a priori kind of hard to understand why I'm doing this, but we're going to say that the potential energy is zero when the dipole is at a 90 degree to the magnetic field. So if dipole looks like this and my magnetic field is pointing that way, eventually it's going to turn that way. But this is when it has no potential energy. So that's the definition that we're going to make. So the reason we're doing this is just because I want an expression for energy, not a change in energy. So this is my final energy, or I'm just going to leave off the subscript, and then this would be my initial energy. So the change in the energy is just like that. So that means I can write my expression as just work is equal to negative U. It'll just make things a little bit cleaner. Okay, so what is work? In this case, we are looking at a torque, not a force. So we're going to need to use angular work instead of linear work, the definition anyway. We know what the torque is. It is the magnetic dipole cross the B field. So let's plug that in. And we're just looking at, right, energy is just a scalar. It doesn't have a vector orientation. So let's get rid of the vectors and write it in terms of the magnitude of the cross product. And one little tricky thing here, what direction is this thing going to turn in? If I have my magnetic field going to the right and the dipole was initially up, it's going to turn that way. And based on the way that we measure angles, normally it's zero, increasing, increasing, increasing. So this is positive d theta. This is negative d theta. So that's why I'm including this little negative right here. Kind of summarized right here. I crammed it in between the magnetic field lines. So once we do this integration, we've got a negative arising from the sign being integrated. And this negative is just coming down here from the orientation of how the angle changes. And of course, we're not integrating with respect to anything in particular, so just an integration constant, which we're ignoring for the exact same reason that we can set zero for the potential energy to be anywhere. So now we've got this expression, the change in the potential energy, and I'm just going to say that that's U instead of, I'm defining zero to be my initial. Now I'm going to bring in I shouldn't have made that so omega looking. That's supposed to be a W. That's just the dot product. So torque had a cross product, energy has a dot product. Makes sense. Dot products are scalars. So why does this actually make sense based on my definition up here? If I were to plug in 90 degrees here, this would end up being zero, right? So that actually makes sense. And also, what is the stable configuration of this system? It's when the dipole is at the same in the same direction as the magnetic field, which is angle zero, and that's as big as this can, well, because there's a negative, it's as small as it could possibly be. And when is something in stable equilibrium? When its potential energy is minimized. Just like when something's on the ground, its potential energy is zero. That's as low as it can get. So you say something's in equilibrium when its potential energy is minimized. Okay, so we have an expression for this, right? We found something for that. So let's plug that in. So we're plugging in the expression that we found for the magnetic moment in terms of the angular momentum. So plugging this in, it looks like some of our negatives are canceling here because that was related to the angular momentum negative, in an opposite direction. And now what we're going to do is get rid of these vectors. So remember that a dot product is just a projection. So if my angular momentum is at some angle like this, but my magnetic field is pointing up in the z direction, we'll just say it's completely arbitrary, but let's just say it's in the z direction. And that means we can just pick out the z component of this vector. So projection, what does that mean? If I put like a little eyeball over here and I stare at my vector in the direction of the line that I'm referencing, this B line, this region right here is how much of that vector relies on the other vector. So that's, you know, physically what the dot product is doing. It's a projection. How much of one vector is on the same axis as the other vector? So just changing this vector to a B, I'm just going to say that's my magnitude of the electric field, magnetic field. And this is now my Z component of the angular momentum. And that is a quantized quantity. So now let's start thinking about this in terms of the quantum number ML. Let's plug this in here. There we go. So this has very specific, only allowed quantum numbers. Uh, just reference, we've got some multiple M's here. There's a reason there's a little E on here. ME, mass of the electron, M, quantum number, magnetic quantum number. Okay, so again, we're ignoring J's in the lab manual. J is technically the addition of L and S, the quantum numbers. We are not dealing with the spin quantum number. If we were doing the anomalous Z effect, that's a little bit later in the textbook, I think. I think it's in the same chapter. Nope, I guess not. Yeah, it's probably going to start talking about spin in chapter 8. Yep, here's J. And there's the anomalous effect. Yeah, so we are not doing that. So no worries about J, just switch it in your head to L. Okay, so remember, we are looking for a change. Oh, look at that. We are back at our equation 1 for the lab manual. We're plugging in ML H bar for the angular momentum. B, lab manual just puts the B inside the parentheses for some reason. We'll be modifying this equation in a little bit because that's actually not going to be super helpful for plotting and what we're actually measuring in the lab. There's a little bit more steps. Okay, so we are looking for a change in the energy due to the magnetic field turning on. And what else is changing? The magnetic quantum number. So these have also a quite specific, and these are, something that come from everything that we've reviewed so far is like the wave description of quantum mechanics. Deriving where these selection rules come from, I'll show you where they are in the textbook, but they're way more easily done with matrix mechanics. One of the German lab manuals I put in the extra files. Which one? This one. This one talks about that. Again, I don't think that's absolutely necessary for us to talk about. But it turns out, where is it? 3, 6. Turns out there are only so many allowed transitions. And this is, yeah, it's not derived at all in here. So we're just gonna say that these are the rules until we get to, because I don't think you actually touched the matrix version of quantum mechanics. That is something you'll touch in the upper level. course, pretty much the entirety of that course. That's due to Max Born and Heisenberg. So Schrodinger was waves, Heisenberg and Born were the matrix version of this. So this is what we're going to be looking at. There are only so many allowed transitions for this quantum number: -1, 0, and +1. For our particular experiment, we are only going to be observing these two, -1 and +1. This one, because of the geometric optics of our experiment, we will not be able to observe that one. These two are going to combine simultaneously. It's going to be a superposition of these two. So what we're actually going to be seeing for this delta ML is the number 2. So 1 minus -1. So that's a little bit, it's a lot. Both of these lab manuals, 1 and 2, describe that very, very well, but it's quite complicated. And I'm not, I think I put it here in the lab manual as well. Yeah, I'm not expecting you to do a full like polarization analysis for this lab. I think that's a little bit much. So just take that for what it is. We are looking at simultaneously the circular polarization because a quarter wave plate and a linear polarizer. Where is it? Oh, it's figure 4. These two things combined with each other in particular orientation create a circular polarizer. I think that's enough description of that. We've got two circular polarizers, one going one way, one going the other, and we're going to observe both of them at the same time. So now our equation becomes, instead of leaving this ML or delta ML in here, this is going to be 2. So let's plug 2 in here. That gets rid of the 2 in the denominator. So what are we doing? We are trying to calculate the change in the energy through the shifts that we're going to observe in the spectral lines. So basically what we're going to see, um, let me show you. I mean, you'll see it in the experiment videos that come in a little bit, but this one has a decent figure for it. That's a great figure for the circular polarization stuff. Here we go. So these are the lines that we'll see when B is 0. And then depending on the polarization that we have, you'll see different things. So this one would be when so there are a few little dashes on the this thing that I was talking about, the quarter wave um, linear polarizer. If you orient, let me just look at what these are. I'll show you exactly what these figures correspond to. No magnetic field, so we're just seeing the diffraction pattern, bright fringe, bright fringe, bright fringe, bright fringe. If you orient the physical slit, so there are two Sharpie lines. One is short, one is long. The long one is the main one that we're going to be looking at. This is the main one we're going to be looking at. Um, So if you have the long black Sharpie line oriented up, you'll see this. These lines will split into two, and that's what we're seeing. We want the two different lines to be the gap that we're analyzing. That's the two circular polarizers combining constructively. If you put the physical slit, so that's when I say physical slit, there's like an actual, it's not a Sharpie line, it's an actual slit in that polarizer. If you orient that upwards, you'll see this pattern. They will split into 3 lines. It's basically no polarization. This one, it would be the short black line, the short black Sharpie line. If you do that one, you won't see any splitting. So that's just a little bit of a summary, but we're not going to be, I don't expect you to explain to me why the different splittings are happening. Just we are doing this one. Figure B, where our spectral lines are going to be splitting into 2 spectral lines, and we're going to be measuring the gap between those 2 things. Okay, so energy. How are we going to determine the energy gap Well, we're observing things physically, like we're looking at things and observing them physically. We need to figure out a way to look at those lines and get a physical observation. A lot of geometric optics are going to come into play, but ultimately we need some sort of uh, shift in the wavelength because that's what the interferometer is going to be able to provide us. So let's take a few steps to get there. First thing we're going to do, we are observing spectral lines, so light. So the shift in the energy is going to be just like from before with the photoelectric effect, Planck's postulate. Energy of the photon, Planck's constant, frequency of the photon. So what's changing? Planck's constant, that doesn't change. The frequency just changes. And one thing that'll make this a little bit easier for us to analyze, um, this is Planck's constant. This is the reduced Planck's constant. So let's get that out of here. Just have, one solid thing. So let's plug in some things. H is equal to 2 pi h bar. That's just reversing the definition of the Planck's constant. Frequency is related to angular frequency, and that's the only reason I'm introducing this is so that we can get rid of this 2 pi that will have arisen due to converting back and forth between the reduced and the regular Planck's constant. So I'm going to write this in terms of angular frequency. So if I plug this in, I've got change in the angular frequency over 2 pi, and then my Planck's constant has become 2 pi reduced Planck's constant. 2 pi's canceling out, and then my reduced Planck's constant cancels out. This is the equation. This is like what equation one is meant to say. We are going to be plotting the change in the angular frequency on the y-axis. We're going to be plotting the magnetic field because that's going to change as we change the current on the x-axis. And the slope of that is a well-known value, the ratio of the charge of an electron to the mass of an electron. And so we can compare that to the actual value for it, 1.75882, 10 to the 11th coulombs per kilogram, and find a percent error. So onto the experiment. B, for these very, very complicated magnets, you should see Dave's work for this. It's wild. It's already been done for us. These are very, very complicated magnets. They're not just coils. They're like these weird pointed. It kind of looks like a house from the side. It's like a rectangle with a point on it, and there's two of them oriented towards each other. Incredibly complicated. Lots and lots and lots of Biot-Savart law pages in Dave's notebook. He has impressively calibrated this for us. It is down here in this figure. So that is the magnetic field. So that means as we shift the current, that's the dial that we're going to be turning. And that's just something we're going to read off from here. So we're going to increase this from 0 to 1 to 2 to 3, all the way up to 20. And that will change the magnetic field. That's our independent variable. Next thing we need to do is figure out, so here's where some funkiness comes into play. Bear with me here. We need to figure out how to calculate delta omega. So delta omega in terms of, converting back and forth between linear and angular has this factor of 2 pi. So a shift in the frequency can also be quantified as a shift in the wavelength. And this whole procedure that I'm doing right now is towards getting to, I'll just spoil it a little bit. We'll get to this equation in a second. This insane formula, which more or less is all due to the fact that we are using this interferometer. So I need somehow to calculate this in terms of the shift in the wavelength, because that's the actual equation that we have based on the interferometer that we're using. So I'm going to express this function in terms of wavelength. So I say function, and the reason for that is as follows. If I say that f is a function of lambda, c is just a constant, then I can write this, with a little function nomenclature here, c over lambda. Nothing changes about the equation. It just makes it a little bit easier for me to figure out what I need to take the derivative with respect to lambda. So if I take the derivative of this function, how do I do that? I'm just going to pull the constant out and take the derivative of lambda to the -1, right? That's what something in the denominator is. And that just makes it easier for me to rationalize what the derivative is. You decrease the exponent, bring down the sign that you changed it from. So the derivative of frequency with respect to wavelength is c over lambda squared with a little negative sign. So now I can write this. And now what we're going to do is we are going to shift this infinitesimal quantity to a finite quantity, because what is a derivative really? It is the limit of a finite quantity, rise over run. It's the limit of that as this approaches zero. This is already really, really close to zero. Just to give you a little bit of a spoiler, the delta lambdas that you're going to be evaluating are like 10 to the negative 11th, 10 to the negative 12th. That's already pretty close to zero. So instead of keeping this derivative around, we're just going to say that it's pretty darn like that approximation is a very, 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 very good approximation because our values are already so small. So we're just going to use this as our equation. Delta F, delta lambda, negative c over lambda squared. We are only caring about the values of these things, not the fact that as frequency goes up, uh, wavelength goes down. We don't, it doesn't matter for our purposes. So we're just going to take the absolute values of everything. And so we end up with this equation. The change in the frequency, c over wavelength squared, change in the wavelength. So now we can plug that into this equation, and we have the dependent variable that we want to analyze in terms of not just the frequency, but the wavelength shift. The wavelength shift is what we can actually determine based on the geometric optics of this LG plate. Holy crap, it's intense. The derivation of that, let me show it to you. I think I have this open. Um, this comes from a textbook by Emil Wolf, a really amazing atomic physicist, and Max Born. The Max Born that I said earlier. That Max Born. So where is this? That Max Born. Matrix matrix formulation of quantum mechanics. But also the guy who the very first equation we started with today. So let me just scroll through this very quickly to show you why we're not going to be analyzing geometric optics. Yeah, yeah, exactly. Yep, yep. All right, let's go down to the the actual FG plate. Where is it? Oh, here it is. Insane, 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 insane. Optics is crazy. Just FYI. Here's the final equation. This final equation is what is in the lab manual. Same exact equation 2 is equation 80 in this very, very complicated textbook. We are going to make an additional simplification. This term right here is something called dispersion, which we are not going to be dealing with because we're measuring things so locally. So I'll show you in the experiment part of the video, but we're going to be measuring things not across the entire LG plate, but very, very small. So dispersion is not going to be something that we have to deal with. So we're just going to set that to zero so that this equation reduces a little bit. So let's talk about what this equation is all about. Lambda is the emission line wavelength. So that's the emission line that we're analyzing without any perturbing B field. It's going to shift based on the fact that the magnetic field is going to turn on. N is the refractive index of our particular LG plate. This has been all itemized for us right here. D is the thickness of this plate. Let me just so D would be this thickness right here. N is based on the actual material of that LG plate. Delta A, so here's where we're going to start actually talking about what we're measuring in the lab. Delta A is the distance between the lines before the splitting occurs. So it kind of looks like this. Let me show that this is delta A, the distance between the diffraction pattern spectral lines. So delta A, But notice they're different numbers. So let's say this right here was the brightest fringe that I want to be analyzing my delta A's or lowercase delta A's for later. Capital delta A is basically going to set a calibration length for me. So those two delta A's, they're basically the distance between adjacent lines. They are not equal to each other. So the way that I did this was I just took the average of them. I measured that in Inkscape, I measured that in Inkscape, and then I took the average of those two values. So that's my delta A. Kind of looks like this. Our diffraction pattern will be oriented not like this, but like this. The lines will be it kind of you've got like these three long lines. I picked the one in the middle. That was the brightest in my case, and then some like reduction down here. So that's what capital delta A is. Lowercase delta A is the actual shift in these bright fringes. So I picked this one. That was the brightest fringe that I could see. And I mean, the cameras that we're using are not great. So very low. It's like 1 megapixel, which is wild. They're like 15 years old. This little delta A is the distance between those two gaps that's going to be changing. Delta A is the same for the whole experiment. I really should have changed the symbol. Uppercase delta A, capital delta A is the same for the whole experiment. Lowercase delta A is effectively going to be our independent or our dependent variable. And I wrote 5 amps because that was the first current that I could actually see. Because our cameras are so old, I couldn't see any splitting from like 0 to 5 amps. At 5 amps or 6 amps, I think, is when I actually first started to see this. All right, we're almost done. Let me just show you roughly what my Excel sheet looked like. These are just constants. They're itemized above. Constant, constant, constant. Measuring this, and I want to do 2 measurements and get the average of it. So this is staying the same the whole experiment. And then I'm increasing my current in integer values. Again, I couldn't get anything less than 5. And then the magnetic field corresponding to that based on this formula. And then the shift in the wavelength based on this formula. And oh, I'm missing a column here. Sorry about that. Obviously, you're going to need a column for lowercase delta A. So in between these two, put another column that's lowercase delta A. Sorry about that. I'll fix that before I upload this. Then, based on this, I can calculate the shift in the frequency because now I have delta lambda. Those are just constants. So that's the next column. And then finally, with this equation, I can get the shift in the angular frequency. So that'll be this column. And then remember, what equation are we modeling this on? This one. So once I have my delta angular frequencies and I have my different B values, I can plot them, y-axis, x-axis, and get the slope. So I did actually do some like error propagation for this lab based on the fact that the pixel measurements are so hard to get right. It turns out that just using Lineast actually provides you a bigger uncertainty. And so it's a little bit more reasonable. Like it is so, like if I shift, let's say I measure one of my little delta A's to be 20 pixels. If I change it to 19 pixels, my percent error changes by like 2%. That's massive. So I think it's totally fine to just use Lineast for this lab. So just unweighted linear regression using the built-in standard deviation error. Totally cool. Okay, so yeah, I will change this a little bit to include a lowercase delta A, and there we go. Alrighty, how the heck does this lab work? Not much to do, honestly. Everything's already kind of set up for you, so you don't have to really plug anything in other than the outlets. Underneath here, this is here for protection. You really shouldn't be looking at this thing for a long time, but I will show you on the video. Once we flip these switches. Ooh, spooky. Cool. Okay, so let's not look at that for a while. That is our cadmium source. Okay. And I've already aligned the camera and the telescope, so that should give you very good data. So let's actually see the data. I've got it set at some random current so that we can actually see the splitting occur. But let's just leave it there until we actually see it, and then we'll actually change things. Okay, so I have downloaded everything that we'll need. First thing we need is this program, Modic Images. Very old program because these cameras are very old and the resolution is not great. So, you know, if you can get less than 10% error, that would be fantastic. So here's the kind of main, you know what? Let me raise this thing up a little bit. This angle's kind of crappy. Much better. Okay, so this screen right here, not terribly important. The only thing that we're gonna need for this is over here. You see my cursor over here? This is going to be where our images appear. So just to make sure that we're actually doing things. First things first, we want to be exporting these things in a specific way. We are ultimately going to be using Inkscape to analyze things here, just like Bragg. But Inkscape will not, I have no idea what that file is. It's like a Nintendo NES file. I have no idea why that's the default. Switch that to JPEG. And to make things easy for ourselves, let's name this Zeeman. Image size, big as possible. Okay, we're not using auto capture, it doesn't really matter. We don't want that, we want the file name. Okay. Nothing else we need to do here. We are gonna head over to capture. So you'll notice up here in the left-hand corner, we've got Modic X and nothing else. That's because camera isn't plugged in yet. So we'll plug this in, and usually you need to close this capture window before it actually reads anything. So now that we plug that in, you will see a green light on the camera once you plug that in. So I'm gonna go ahead and close this capture window and then reopen it, and it should read the new camera. Yep, there we go. Modic 1.3 MP. So just give it a little bit. There we go. We are seeing stuff. See if we can zoom in at all. Not really. Not much. That's all right. Okay, so we're going to leave exposure on the auto setting. Don't need the keyboard now. Move that up. And what you can do, you can change the gain and offset, especially as you get to higher currents that may be useful. Some other things that you can do, color adjustment. I actually ramped this up all the way. I found that that gave me slightly better data, and you'll see that it takes quite a while for the camera. It took, you know, like a 2-second adjustment for the camera to actually read differently. So color correction I used. Down here in advanced settings, I can't quite remember what I used here. Oh right, remove noise. So let's remove noise so that the camera doesn't jump around. Scale that all the way up. Okay, cool. So we're removing noise, and because we did that, the camera is continuously adjusting. This is the auto, right? It's just kind of work on its own. Let's see what we get. And then after all those corrections, gain and offset are your last two kind of things. We'll get to this setting in just a second. Okay. So right now that gain is probably fine. If I ramp it up, it looks crazy. No, not so crazy, but the more you ramp this up, the less you'll be able to distinguish Yep, see, it takes a while. Basically, we are trying to measure the distance between these two lines at the end of the day. That's our main lab source. So let's put that all the way down. Let's see if, I think 1.3 was probably pretty good. 0.5 maybe a little bit low. So let's just wait on the camera to adjust to this new setting. Yeah, not great. Yeah, too low. So let's very slowly increase this back to around 1.3 where it was. That seemed to be pretty good. Yeah, so maybe these aren't necessary to move around with, because this is roughly what my data was looking like when I did offset. Let's try this a little bit, see what happens here. Apologies, I just looked at my phone camera and it looked like it was bouncing in and out zoom wise. I'm not really sure what that was about. Hopefully that doesn't cause anyone I just clicked on the screen to focus it for a given focal length, but yeah, hopefully that doesn't show up and cause people any motion sickness. Okay, let's just leave things there. That looks all right. Okay, so now let's actually see the phenomena at play. I'm gonna head over here and turn this down to 0 amps slowly. So we're keeping our voltage knob all the way ramped up so that we can actually spin this dial and change the current, because the current is what's going to change the magnetic field. Okay, I'm going to slowly decrease this and you'll see the lines change. So you're starting at 0 amps. So I'm reducing back to 0 amps because I had it at 11 just so that the figure looked decent. And again, as you adjust, not only is it going to take, it takes some time for the camera to show the new stuff. Go all the way down to 0. We're at 0, let this adjust. And here are the unperturbed, no magnetic field cadmium wavelength lines. And what we'll observe based on the polarization that we select, and I'll give you the specifications for this just a little bit. That black line upwards is the one that we'll be using to take data. So let's just stick with that for a while. We'll see, there's some aspect of theory where we can change that to different polarizations, circular polarized and linearly polarized, and see different results. Subject of another video. Okay, so what I ended up seeing, basically what we're going to be doing is the first step is to take a picture at this moment. And so this is going to allow us to calibrate. I will put this at another point in the video, but this is going to be our delta A, just for reference. Delta A, unfortunately, these lines are not separated by the same amount. So what I did when I calculated delta A was I took the distance between these and the distance between these in pixels. So we're not, there's no micrometer here or caliper that we can use to calibrate things in Inkscape, but that's okay because the equation that we're using has a delta A and a Yeah, I really should change the symbol there. Capital delta A and a lowercase delta a in the same equation, numerator and denominator. And so those things are going to cancel out. So the units will stay in meters for lowercase delta lambda. So this is just going to be measured in pixels. So let's see how we actually do that. First things first, before I start capturing things, I want to make sure it's actually working. So I'm going to click this button in the top right corner to make this window smaller. So right next to the X. Oh, it was already in it. So click that, and now drag this to the side so that we can see our images start to appear over here. So now let's check out what this whole capture feature looks like. We're gonna head over to this camera icon. Format as big as possible. We want as much, the resolution on this already is awful, so let's get as much information as we can. As soon as I click capture, a few seconds later, the image that I just captured will appear over here. There it is. So Zeeman was how I named the files, and 1. So the annoying part is it starts at 1, but my current is 0. So that's just something that we're gonna have to keep track of, and I'll talk you through how that works in a bit. So we'll analyze that in a little bit. And what we're gonna do is take data at every single amp measurement in 1 amp increments up to 20. However, what you'll see is that we're not gonna get good data at all until like 5 amps or so. So let me show you what I mean. We just captured an image that will allow us to get uppercase capital delta A. Now we need to get some data for lowercase delta a. So here's what the image looks like at 1 amp. Right now we're at 1 amp, and let's wait for the camera to adjust. Nothing. So we are really not going to see much until around 5 amps, maybe 4. I can't quite remember. Let's see. Let's increase this to. Let's just skip, because I know we're not going to see anything at 2. Let's skip to 3. See if we can see anything. Not really much of anything. It's starting to shift a little bit, but we can't see any distinct lines yet. Yep, nothing. Well, kind of, I mean, barely. I could see a slight dark spot in there, but I wouldn't even measure that yet. Let's do 4, see if we can see anything yet. Starting to see it a little bit. Zoom in here. Starting to see some separation. So I picked my brightest line. So to me, this was the brightest line when we originally started. So yeah, you know what? Honestly, I may actually take data at 4. So disregard that. You can start taking data as soon as you see a gap. And I'll show you how to take data in just a second. I downloaded Inkscape so we can do it on this computer too. All right, let's just, this is basically, you know, we're gonna be taking all these measurements. Let's just increase it to 8, because that will definitely show it. Seeing the line splitting now. Just wait for the camera to adjust for it. There we go. Nice. Okay, so because I'm skipping around here, normally our images over here would correspond to 1 less than the amperage. Like, so you definitely do, just for your own sanity, take data at every single amp. don't skip. So that would mean that 1 corresponds to 0 amps, 2 corresponds to 1 amp, 3 corresponds to 2 amp, and so on and so forth. It just makes life way easier. So you don't get, because this isn't like the Bragg data collection tip that I gave, where you take 2 pictures, one with the volt knob in it and one without, because you're actually taking pictures with your phone. With this, you are not taking pictures with your phone. You are just using this software to get your data. And so I can't see the amp knob. So definitely take data, regardless of if you're actually going to use it and analyze it. Just take the data at every single amp measurement in one, integer measurements. So we're not going to do that for this because I'm skipping around here. So let's capture, and we'll just take a mental note that Zeeman _2 is 8 amps. Okay, showed up. Now let's ramp it up to, let's just do 16. Actually, let's not do 16, because what you'll find, and another reason to do it every amp, is because once we go to 16, like let's see what happens when we ramp all the way to 16. It's very confusing because the lines spread out so much that you can't tell if it was the original line over here or the original line on the other side. Let's wait for it to adjust. And I ran into this too, even when I was, I was analyzing this in Inkscape like I did for the Bragg lab, where I would upload an image, do the measurement, close the image. Upload the image, do the measurement, close the image. I would not recommend that for this one. I would recommend importing every single file and putting a little text label on it, because now these things are all, my phone is not liking this computer screen shutter rate. It's very hard to tell where we even started. They're all just kind of spaced evenly apart. So that's why we're doing that. So anyway, we don't need to take an image anymore. I just needed to see something splitting in order for us to show how to analyze this in Inkscape. Okay, so let me shut my system off. I'm gonna turn my current all the way down to 0. Flip both of my power buttons and head over to Garrett and analyze some things in Inkscape. Okay. Let's zoom out a little bit so we can see the whole screen. There we go. Okay, no need for any of this anymore. X out of this, X out of this. And we already got this in JPEGs, so that's great because Inkscape likes JPEGs. Come on, software, I don't need you anymore. Get out of here. Boo, 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 boo. Not responding. Good, close. Cool, okay. So we need to figure out where the heck these files are because they are buried. So we're gonna go first to File Explorer down here. Then what we're gonna do is go to this PC, Windows, Modic. Let's get a little closer here. Capture folder. These can be deleted, don't need those. And here are our images. This path is so confusing, so let's just put them on the desktop. So you're gonna, once you have, you're gonna have one, Zeeman _1 to Zeeman _21, corresponding to 0 amps all the way to 20 amps. So now they're easy to find. So here's our data. And then we're gonna head over to Inkscape and start analyzing them. New document. And we'll just ignore this white page. I have that other video that will show us how how to get rid of this because, like I mentioned, it is much, 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 much nicer. And in fact, I would say it's required to keep track of things in this lab to label everything and put every single file on this document, not the page. The page will go away. So first thing, let's start doing some labeling. I'm gonna head over here to text tool. Just click somewhere and increase the font of this by a lot. Like, let's make it like 72. Zero amps. Let's make another one. The other thing we were looking at in this particular case is 8 amps. But what you would do is basically make a grid. That's what I did. So this, if you ever want to move something, I would not be able to move anything. This is only going to allow me to edit these text objects. This cursor symbol will allow me to move my objects. So basically I just made a bunch of these labels. I lined them all up, and I'll show you the alignment in another video. Lined them all up, made like based on the fact that I only started at like 5 volts, I had like a 4x4 grid that was what they correspond to, and then uploading all my files. Starting, I would say this is Zeeman 1. This, if I had followed my convention, would have been Zeeman_9 JPEG. So now let's upload our stuff, and let's just get it all the way away from this stupid white page. I'll show you how to get rid of that white page in another video. There we go. Okay, and we're heading over to import. And because we put these on our desktop, very easy to find. From file, nope, just regular. Okay, so here is our 0 amp. And here is our 8 amp. Again, not following the convention. Oh, I should have clicked don't ask again. Oh well. Okay, so now we're back to using our measurement tool, just like we did with Bragg. However, way harder with this lab. So we are going to head to measurement, and I need to figure out how to zoom without I did this on my laptop. How do I zoom? Just scroll, view, zoom. Well, I guess I'll just do that. Plus button. Does it work on a PC? Nice, okay. All right, so measurement tool down here, like before. And this is my measurement of capital delta A. So I'm gonna take 2 of them because the distance, as you'll see, from this to this is not the same as this to this. And I just took the average. Figured that was good enough. So I'm gonna zoom in a little bit so I can see this better. Here's my central line. So I want the distance from here to here. Try to get it at 0 degrees. Not always possible. See, my only options are kind of negative 0.28 and positive 0.28. You can zoom in a little bit. Let's zoom in even more. View, zoom. Oh wait, yeah, plus button. Plus button. This is much easier with a laptop. So you definitely do not have to do this on the computer that we're using for lab. That's only the Modic stuff. I mean, honestly, you can even download Modic on your, actually, no, you can't, sorry. That is, there's a passcode that we have in the department. Oh, nice, all right, so I got 0 degrees. And then I just have to worry about lining these up. I mean, this is what I was talking about. The more I zoom in, it doesn't necessarily get easier to center these lines. So, this up a little bit. I'm just going to estimate where this is in the middle, and then I'm going to zoom out and see, I guess, move it over a little bit. And then move this one over a little bit. If I can get to 0 degrees. There we go. Okay, why is that measuring in millimeters? Yeah, there's no calibration. How would it know how many millimeters that is? Yeah, so if your measurement, mine did not do that. If your measurement tool is measuring in millimeters, ignore, I mean, it doesn't really matter as long as it's doing the same thing every single time. But I don't know that I trust that. Whatever conversion it's using will be the same for every image that you analyze. So it doesn't matter that much, but let's just do pixels. That's what I've been working with the whole time. So let's keep it as pixels. So I will import this number into my Excel. So delta A I will write as 95.71 pixels. That's one of them. Well, let's check. Minus sign, minus sign, minus sign. Do these two red dots look like they're in the middle? This one looks all right. This one, I mean, that's the thing. Like, look how thick that line is. Not really. It kind of looks like it's a little bit to the right of the center of that line. So I'm gonna move it a little bit over. That looks more like it's in the center if I were to analyze this whole line. So 93.78 pixels would be one measurement for delta A. And then this is the only one that you actually need to measure twice, just because these are different. Nope, not quite in the middle. A little bit more. That looks pretty much in the middle. And this one's a lot fainter. And what you'll notice, if I zoom out a little bit, you may be able to see it. There's a defect. You can't quite see it. I could see it when we were analyzing the image a little bit. Let's see over here if you can see it on the 8. You'll probably be able to see it on the 8 amp. See this faint line that goes across the system? And then this line here? Those are defects in the plates inside the Lermer plate, or whatever the heck it's called. I forget how to pronounce it. Do not measure along those, right? You see this shift in the lines? So that means I'm just gonna, for the entirety of my experiment, I wanna be measuring in the same location. So that's why I picked this one, because I saw that kind of line coming down here and this line across. So that's why I'm measuring where I am. So then my second measurement, let's move this just a hair to the right. And get to 0 degrees if I can. 0.10 is okay. That's also fine. So then my two measurements would be whatever I said first, I didn't write it down, and then this next one, 113.22 pixels. Take the average of those, and that is your capital delta A. So now we've got our, quote unquote calibration. Then over here, once we start actually measuring the gaps in between the splitting, so this line here, this one, has become two lines. So then I'm just gonna start analyzing this. And this is my lowercase delta A. And again, the whole procedure is just trying to get these in the middle. Let's see, how does that look? That's probably as good as I'm gonna get. Thankfully, sometimes the measurement tool, this red circle sometimes, depending on how good the resolution is of the picture, it will almost fill up the bright spot. So my delta A for 8 amps, in this case, would be 25.85. And what I'll show you in the Excel analysis part is after we collect everything, if I change one of my, let's say you get 16 good pieces of data, like 0 through 4, you can't really see anything. You start at 5 amps, you get 16 pieces of data. If you change one of these to 25.9, it will dramatically change your value for the ratio of the charge of the electron to the mass of the electron. So it's very delicate, and unfortunately that is a massive source of uncertainty, simply because these cameras are very, very old. and we really should upgrade these. So that is how we're doing this analysis for the lab, at least the data collection aspect, and then I'll move over to the Excel analysis. Hey people, if you are like me and this white background bothers you to no end, the way to fix that, going into Files, Document Properties, and then click Desk, and you see how it's not quite white? You can drag the slider, make it all the way white. Just looks so much nicer to me. Figured it would bother some people too. Just making all my data pretty here using the alignment. So what I can do here is I didn't actually know how to open this window because I'd actually put it all the way over to the left, but you can just slide this out here and the alignment tab will be here. Or you can click over to Object and then open it with this button. So I'm just making my stuff look pretty. And the reason I'm putting these all on the same screen is it is very hard. Once you start to see the splitting, it's easy to tell what lines you're doing the difference between. But once I got to about the 14 or 15, I noticed I jumped. I was, 30 pixels, 35 pixels. And then the next one was like 60 pixels. And I'm like, hold on, something's wrong. And that was because I was analyzing the wrong lines. Right now, it's not easy to tell what lines, the gaps start to become kind of similar. So I probably measured that distance there. So much easier. And so that's when I just uploaded all my pictures. I went to import and I just uploaded everything. And so here, this one's a little bit easier. And I should have mentioned this actually in the Bragg lab because when you take a picture with your phone, it's just going to be a random image 4134. So you should take two images. One image that's includes the voltage that you're currently at, just so that you remember it. And then the next image after that should be the pattern. So for that one, as long as you kept track of that, it wasn't super necessary to put them all on the same screen. But for the Zeeman lab, I would definitely recommend this. So the way that we use the naming convention, just show you this briefly. Where did I put that data? Here it is. Did I call it? Oh, here it was. Naming the files. So we're naming the files, but because the first picture that we take is at 0 volts, that means the 0 volt file is going to be called, where do we go? 1. So notice it goes from 1 to 21. So that means 0 volts. I'm sorry, I keep saying volts. I'm getting it confused with the Bragg lab. 0 amps, 1 amp, 2 amp, 3 amp. So it just, it's off by one. So that's even it makes it even more confusing. So I thought it would just be way easier if I uploaded everything. Oh, I don't want that on there. If I just uploaded everything. So now I'm just kind of aligning things to make it nice before I start analyzing my data. I'm going to shift click all these objects. Then I'm going to align them. And then I will distribute them vertically. And I'm going to do the same thing with these. Then I can drag them all as one object. I could also use, some, where is it, group features up here to make them all one thing, but this is totally sufficient. Group them out so there's a little bit of a gap in between them and align them. Shift click, center them, space them apart.